Hi, Gen Chem class. We are at 21.4 in our exploration of organic compounds today. We're going to be talking about a lot of common functional groups that we see attached to carbon chains. Halides like chlorine, bromine, alcohols, which are OH groups, ethers, and amines. So we're going to learn how to identify them and name them and write their formulas. And we're going to look at a few reactions, not too many though. So the discussion in this chapter starts with the concept of bond order. We talked about bond order a long time ago when we started drawing Lewis structures. The point to remember here is that in organic structures, carbon, for example, is always going to have a bond order of 4, we say. It's going to have 4 bonds to it. Nitrogen is always going to have a bond order of 3, and it has a lone pair in their neutral states. So you can always predict how many hydrogens are going to be coming off them, for example, or how many, maybe this is a carbon chain. Well, we know we have to have 2 hydrogens to fulfill that octet. So I'm going to skip to the next slide here. It has this chart to remind us. And all this chart is saying the total bond order means how many bonds does this need to fulfill its octet. So, well, this needs 4 bonds to something because it needs 4 valence electrons to get to 8. Hydrogen will only have 1. Oxygen needs 2 more bonds to give 2 electrons into its 6 valence to give it an octet. Same thing with sulfur. Nitrogen, we see it bonding to 3 things. Phosphorus, we see it bonding to 3 things. And then X is a halogen, so chlorine, bromine. So what this really means is if I look at a structure like this, we should be able to remember what am I not showing here? These all need bonds here. So I need to be able to fill these in. If I see the structure, I got to think, what is missing here? Well, carbon still needs 2 bonds to something over here. So we need to give this 2 H's. This carbon in the middle right now has 1, 2, 3. So it's still missing 1 more bond. It needs an H. This carbon is still missing 2 bonds to stuff, so it needs H's. Nitrogen, again, it needs 3 bonds to fill its octet. So it still is missing 1, 2 H's. And we don't always see the lone pairs drawn, but it's still better to remember that still has a lone pair on there to fulfill its octet. So it's important just to remember how many bonds these things need to get the correct structures when we're talking about functional groups, where we have halides and phosphorus and sulfur and oxygen, things like that. So this practice problem is very similar to what I just did. It says complete the following structure by adding all the necessary hydrogen atoms. So go ahead and pause the video and try this one out. Okay, let's examine each one of these. Right here, we are missing a bond. This needs an H. This one in the middle, this one already has 4 bonds. There's 3 here and 1 here. So that actually is fine right now. What about this carbon? That has 4 bonds because it's got a double bond here and 2 more. Oxygen, this looks great. It has its 2 bonds. Notice the lone pairs are still there, they're just not explicitly shown here. This carbon needs 2 more to get 4. This carbon here needs 1 more. This carbon here needs 1 more. And this nitrogen here has 1, 2, so it's missing 1. And it has a lone pair. And this carbon is missing all 3. So I want to show you how I would turn this into a skeletal structure. And actually here, before I do that, I'll give you another practice. Let's draw another structure that's incomplete. What if I had, actually, you know what, before I do that, I want to turn this into a skeletal structure. And skeletal structures are kind of like the previous version of this, where there weren't all the hydrogens shown. So if I were to draw this in a skeletal structure method, I still show single and triple bonds. Then I'm going to show a bond to this carbon atom here. Oops, I'm going to label these actually. One, two, three, four, 5, 6, 7, 8. We haven't done a lot of skeletal structures yet, and I don't think we really do in this chapter, but I want you to get used to seeing these going forward. So here's where I wouldn't draw all these carbons out. So instead, let me start numbering these. This is carbon 1, 2, and this spot here. I don't actually show the carbon. At just any kind of inflection point, I know there has to be a carbon there though. So I'm going to continue on here with number 4 to number 5 to number 6, which is another carbon, to number 7 to number 8. So what did I just draw? Did I lose a carbon here? Oh, yeah, I added a carbon. After 6, 7 is a nitrogen. There's my nitrogen, and finally my carbon. So this would be the condensed skeletal structure. So notice also I had to arbitrarily make this a trans bond. This doesn't show us whether this is a cis or trans bond. So I just arbitrarily called this a cis bond, as in the alkyl group is on the opposite side of the double bond, and the H's are right here that I'm not drawing. So why do we do this? Well, we do this a lot because it takes a long time to draw something like this. So we represent molecules most of the time like this. So using our bond order idea, we have to remember that what's not being shown is going to be there. So for example, I left these carbons as carbons. Sometimes though, you won't even see them there. You'll see a skeletal structure where you will literally just see, it looks very weird for triple bonds. 1, 2, 3. Looks weird, right? That is actually the most condensed structure you can draw here. It looks very odd, but this says, okay, I know there's a carbon there, and I know there's a carbon here. So what am I not showing? Well, I'm not showing all the carbons and I'm not showing all the hydrogens. So really there's got to be an H here. There's an H and H coming off of here. There's one H coming off of here, one off of there. Nitrogen's missing one more bond. And then this over here is missing 3 H's as well. And then we also have these lone pairs. So notice a lot of the information goes away when we draw these condensed structural formulas, but they all show the same information if we remember these type of bond orders. So there's that practice problem, the one that we just kind of went through here. So that's recognizing how many things need how many bonds. So let's move on to the functional groups themselves. Basically, functional groups are molecules that are not carbon and hydrogens. They have specific chemical properties, and we call them heteroatoms. That's an atom other than carbon or hydrogen, and or an unsaturated carbon. So functional groups are either things like chlorine, bromine, OH, NH3, etc. Or if you see a double bond, we actually call that a functional group. Or a triple bond we refer to as a functional group. These are basically like the reactive centers of molecules. They're a lot more reactive than just the carbon-hydrogen chain, so they're very important to identify and name. So alkane portion, relatively unreactive. Functional groups are the centers of those reactions. When we have, for example, let's say we have this. This is ethanol. This is the functional group, and this is the alkyl chain. We call this group, this general alkyl group, or the parent alkane, it's often referred to as the R group. So if I want to draw the general form of an alcohol, I would just say it's an ROH. Any alkyl group that you see, and if you have an OH on it, then the whole thing we refer to as an alcohol, or this group is a hydroxyl group, an alcohol group. So we use the word R for just generic, some sort of generic substitute when discussing alkyl groups. And if there's multiple R groups on something, you'll call them R, R prime, R double prime, things like that. So we like to name molecules given what type of functional groups they have on them. So if we look at this next one, it says identify the functional groups, not name them, just identify if they are there, and then what are the R groups? in these molecules? Do you see any functional groups here, and do you see any R groups in these molecules? I do. I see some functional groups. In this molecule here, this OH group would be our functional group. Actually, you know what? Let's just call these FGs. And this would be my R group. Going down here, we actually refer to this whole thing, not just the double bond in the center, as the functional group. So it includes the carbons that it's attached to and the hydrogens that are attached to those. But that's a little bit nitpicky. You could really just say like, oh, it's an alkene, it's a double bond, that's a functional group. And this is the R group over here. Down here, we actually have this alkene between carbon and oxygen. We haven't really called this anything yet. This is technically a carbonyl functional group, but we haven't identified those yet in this chapter. But this section would be my functional group here. And then we have an R group on each side there. In the book, yeah, it uses this highlighting scheme to show that same thing that I showed there. Okay, let's actually get into some of these specific functional groups. First, we're going to look at the organic halides, which we have seen previously when we talked about alkanes. So it's a hydrocarbon with at least one of these, F, Cl, Br, or I. So the naming are pretty simple. Again, you just need to look where it is in the compound. Now, if I draw this out a little bit better, so this is CH3, CH, Cl, CH3. I don't have to do this, but I like to draw these out just to get a better picture of them. So all we have to do here for this one is count 1, 2, this is a 3 long chain. So it's a propane. And we say, where is that item? It's at the 2 position. 1, 2 specifically. So this is 2-chloropropane. The other prefixes would turn into fluoro, U before O here, bromo, and iodo, if you saw those on one of these compounds. To show you some real examples of these, the book shows DDT, and I actually added in this one to not get confused between the two, because sometimes I get these confused. DDT is an organic halide. Here's the structure, and notice this is somewhat condensed skeletal structure. We see our benzene rings with no hydrogens or bonds being shown, but a lot of chlorine groups on here. So in general, we would call this an organic halide. DDT is just an acronym. I don't actually remember the full name of this. This is or was used since late 1800s, early 1900s as insecticide for agriculture. We learned later on that it's very bad for the environment, very bad for animals, things like that. So it's pretty much banned everywhere at this point, I believe. It could still be being used at specific countries, but pretty much we don't use this anymore. Not to be confused with DEET. I wanted to make sure that was just in there. This is an insect repellent. We use this all the time. This is found in insect repellents. And it is called NN-diethyl-3-methylbenzamide. That's a lot. That's a mouthful, but actually, this is the systematic name for this. It shows that there's on the N position, I've got 2 ethyl groups. At the 1, 2, 3 position, I've got a methyl group. And then this, kind of like benzene, this is called benzamide. So it actually gives you all the information to draw that molecule. You won't have to name something like that in this course, but I thought I'd just show you the name for that molecule as well. This is the ball and stick of this compound here. Kind of shows you the geometry and shows that these are flat benzene rings. And this is our tetrahedral center here for the carbon. So there are some examples. That's an example of an organic halide. And how do you produce these? Well, you take these very reactive halogen gases, and with heat as well, you can replace one of these H's with a halide. So again, this X always means some sort of halide, one of these over here. So, or for a double bond, remember we can do an addition reaction across the double bond and actually add an H and an X to that. So that's when we have our, our addition and substitution reactions. And notice, this is from the alkane section, if you have excess of this halogen, like a whole lot of it, you can actually end up replacing all of the hydrogens. So you go from CH2 or CH4 all the way to CH2X2, CHX3, or even CX4, like CCl4 or something. So you're just replacing hydrogens with those halogens to produce those. Another example of one of these is called Freon, one of the Freon agents. Carbon, Cl2F2. And it's a really unreactive molecule, very stable molecule. And it used to be used as refrigerants and for a lot of industries. But this is really bad for our ozone layer. The ozone layer is a layer at the top of the Earth. Here's our Earth. Look at that beautiful drawing of Earth. Way up here is O3, and that blocks harmful UV radiation. This compound can come in here and break down the ozone. So we've really tried to steer away from using chlorofluorocarbons, CFCs, over the years. But this was a very common chemical used in many different industries. So that's number one, the organic halides. That's first. Now we're moving on to alcohols. Oh, look at that. I didn't know that reached down high into the bottom there. Kind of weird. So alcohols have the OH group, the hydroxyl group. We've seen a lot of alcohols already in chemistry, but now we're going to get a little bit more specific about them. And methanol is the simplest alcohol. You take one carbon and you replace an H with an OH, or CH3OH, as it's generally written as. That's the simplest. So you can form these by reacting alkenes with water. That's one way you can actually get to that point. So for example, if I had carbon attached to another carbon, H, 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 and H, you can add this HOH, water, across this double bond and produce an alcohol. So that's one way these can be formed. Alcohols are not really good bases in general. So if you just see an OH group like this, not really a good base. They don't ionize very easily. So fairly inert. And it's not like the hydroxide ion. Remember, like sodium hydroxide, when you put that into water, you produce Na plus and OH minus. This is a very strong base. This wants to get back to water. This group does not fall off of that very easily. This is not going to ionize like sodium hydroxide is in water. So this just stays intact, but it's very soluble in water. Alcohols are very soluble in water, like ethanol, the one that we use in beer. And because of that, I wanted to kind of, after we look at the naming, I have some other graphics to look at. But how do we name these? Just like naming where the chloro or bromo groups are, we need to just find where they are on the molecule. So in this case, this is a 1, 2, 3 long chain prop, and we just change this to anol. So at the 1 position, we have an OH group. So we say this is 1 propanol. 2 propanol would be if I connect this to the second carbon right here. So this is 1, 2, 3 prop, 2 position, 2 propanol. And one more example, 2 butanol over here. There was an older system, and we still see this. So for example, if I draw out CH3CH2OH, this is ethanol, the alcohol we find in alcoholic beverages. The old naming system, we would just call this ethyl group alcohol. So we would call this ethyl alcohol or methyl alcohol. But this is the systematic name that we use now for these. But you'll still see these pop up, methyl alcohol or ethyl alcohol. So I wanted to just kind of remember, through the process and what other functional groups we find in compounds in beer and vodka, things like that. So if we look at the one for the chemistry of vodka here, fermentation is where the yeast is going to be reacting with the starches in whatever raw materials you're putting in, and it's going to consume those and produce CO2 and alcohol. So then distillation comes and we concentrate this down and dilute it with water to get to the correct amount of percent alcohol. So there's our ethanol. That's the principal alcohol found in the alcoholic beverages. There are also some impurities in this process. Sometimes you can get a little bit of methanol or a little bit of propanol, and these are not good for us. So you need to be careful in the distillation process so as to not get these impurities that come from cheaper, like different kind of grains, things like that. And then sometimes you have to add things. So citric acid, for example, this is a compound with a whole bunch of alcohol groups. There's one there, 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 and there. These are actually carboxylic acids, like acetic acid. So this is actually ionizable OH groups. They have to be next to one of these to do that. So sometimes you add those into the alcohols, but otherwise pretty clean. Beer, on the other hand, has a whole lot of other compounds that give them color and flavor and aromas, things like that. Yeah, let's see. You'll notice there are some alcohol groups on this compound found in hops. We've got esters, which we're going to learn about too. An ester is an alcohol group next to a C double bond O. We're going to talk more about those. Esters give a lot of aroma and flavor to a lot of different compounds. This isoamyl acetate is one you find in bananas, and this is ethyl hexanoate is one you might find in apples. You'll also find esters used in candies as flavoring agents, or sorry, the flavors. They'll take the substituent that they find in bananas, for example, and they put that into banana Laffy Taffy. So banana Laffy Taffy, banana flavored things. This is the quote unquote artificial flavored, but it is the same compound you would find in bananas. So just wanted to connect some of these organic structures to some everyday items. I mentioned this, if you see an R group attached to an OH, that's the general structure of any alcohol. And so because of that, we really think of alcohols at the OH spot. This is where any reactions are going to occur, they're really going to react there. The alkyl portion are not very reactive. If you put an alcohol in with a reactive metal, like sodium or potassium, those first group elements, the alkali metals, you produce these corresponding salts and H2 gas. So this is a very vigorous reaction. So you produce these compounds like this. So instead of, let's actually use ethanol as an example. And we add sodium to this. This is really reactive, and we actually are going to ionize this. So we're going to get CH3, CH2O minus Na plus. That's a really strong compound. This is a really strong base. Strong base, what we produce. Sodium ethoxide. So you got to be very careful with these metals because they'll always react very strongly with these alcohol liquids. So that's one reaction they go under. These are really powerful bases, and they're used in organic chemistry in synthesis. I actually made my own sodium ethoxide quite often in graduate school. Other reactions of alcohols. If you react an alcohol in the presence of something like a strong acid, you can actually create a connection point between these two alcohols. So notice, let's number this R1 and R double prime, R prime and R double prime. Those will come together to form this compound. This is a new compound. This is an ether. So notice we dehydrated this, so to speak. This HOH connects to form water. So water is a byproduct there. So this is an ether, ROR or ROR double primes. These don't have to be the same. For example, this is taking 2 molecules of ethanol, reacting acid here to get ethoxyethane. This is a new ether. So we've got an ethyl group attached to an oxygen, and on the other side you have an ethyl group. Again, you could react ethanol and methanol together if you wanted to, HOCH3, for example, and you would get an ether. How do we name these ethers? Well, let me just draw another one up here too. This one, we see an R group, an O, and another R group. So we have to know that's an ether. So what we do is simply look for the smaller one. This in case is a methyl group. And we call this methoxy suffix. And then we just name this group. This is ethane, the propane chain. Whatever that group might be. In this case, it's a propane chain. So this is methoxy ethane. The older system would have just called this methyl ethyl ether, but this is the more proper name that we're going to use. So look for the shorter chain. We saw this again, maybe we saw whoops, this should be CH2. So if we saw this, we should recognize we have an R group here and an R group here, and it's connected to an oxygen. So this is an ether. So we're going to look for the smallest chain. In this case, it's an eth group, 2 carbons. So we call this eth oxy. And then we'll just name this propane chain. This is 1, 2, 3, 4 butane. Ethoxy butane for that one. And interestingly, ethers and alcohols can be structural isomers of each other. So this next slide shows C2H6O. That is the chemical formula for ethanol, but it's also the chemical formula for methoxymethane. So it's this rearrangement. So it's instead of this chain here, the oxygen is in the center. Very different compounds for sure, but they happen to have the same molecular formula. So those are actual isomers of each other. Next one is just doing a little bit of practice, but remembering what type of reaction this is. So this is taking an alcohol plus an alcohol. Alcohol and an alcohol group, alcohol compound. And remember, we're using this. Think of this as the dehydrating. We're going to get water as a byproduct. So to do these, it's nice to draw them or write them out where the OH groups are next to each other. And we're going to lose a molecule of water and then make a new bond between that oxygen and that carbon. So to write that out, O, and then this is going to go away, and we just write out what we have left, plus H2O. And there we go. So how would we name this thing actually? Well, same process. We'll look for the smallest chain, which in this case is ethoxy again, so eth-oxy. And then what is this one? 1, 2, 3 for propane, ethoxypropane. So just a little bit of practice, recognizing reactions between alcohols. Okay, almost done here. Also shows this is ethanol, this is 1-propanol to give ethoxypropane plus water for that one. Last classification are amines, and we've seen one amine, ammonia, it acts as a weak base. And yeah, these are reactive parts of molecules because these lone pairs that can go out and do chemistry. So we have an ammonia plus an R group to give us an amine. So you would have RNH3, for example. Some alkyl group could be a ring, it could be whatever. So we have 3 forms of these though. They can be attached to 1 R group. They can have 2 R groups coming off them or 3. Look at that on the next slide. Yeah, so, I already mentioned this, I suppose. So CH3NH2 will react as a weak base in water and form these type of products. So the 3 classes, though, they're very different in reactivity, is we have primary, secondary, and tertiary. The only difference is this has 1 R group coming off of it. This has 2 R groups, and this one has 3. Again, there should be a lone pair in all these as well. So primary, secondary, tertiary amines. These are more reactive. They have more electron density from these carbons. So this is a more basic, more reactive species. And I wanted to show you a couple of compounds that have these amine functional groups in there. Also a variety of functional groups that we've talked about, especially because this compound has been coming up in the news a lot. These are 2 drugs that are used to treat malaria, the disease that comes from the mosquitoes, malaria. So quinine has been around a long time. This is found actually as a flavoring agent in tonic water. And hydroxychloroquinone is a compound that's been in the news lately. Notice they kind of share this core down here, and they're quite a bit different on the top, but they do have similarities in that they have an amine here, OH group, and this core looks very similar. So this is not been found to treat COVID-19. Some people thought for a little while that this might be effective. So far, we haven't had any systematic peer-reviewed studies, but the studies so far show this is not a great treatment. So don't go out and buy a bunch of tonic water. Don't use this unless your doctor prescribed it. But what kind of functional groups can we see on here? This is an ether, right? This is a CH3 group over here that's not being shown. So that's our ROR, R prime. This is basically our other R group, whatever this is over here. So that's an ether. We've got an amine right here. What type of amine is this? Well, this is an H that's not being shown. This is an R group. Whatever this is an R group. Oh, actually, sorry, there's not an H there. This is a weird structure. I lied because it's got this thing going out the back, this and this. This is a tertiary amine. Sometimes you'll see the word 3 with a little circle, tertiary amine. We've got an alkene over here. This we have an H. Oh, actually, apologies. This is a double bond, so there's no room for an H. We've got a halogen over here on this, another amine, another amine, another amine, OH group. So this is a secondary amine. So now hopefully you'll be able to see some structures out there and realize kind of a little bit of the reactivity of some of these sections of the structures. These are going to be reactive centers. Chlorine is going to draw a lot of electron density out of this structure. Oxygen can do some reactions as well because it has lone pairs. So once you really start learning about different functional groups, you start to realize how these might interact with other species. Alkanes, we can do reactions there, right? We can do addition reactions across this double bond, reacting it with bromine or chlorine or with acids, things like that. So hopefully you're starting to get a lot more variety of understanding about different organic compounds and realize how they are everywhere in our society. We see them here with drugs. We see them in our foods, our alcohols, our flavorings. We see them in things like these refrigerants that were used for years, pesticides, insect repellents. Everything comes down to organic chemistry. So really important to learn. And I hope you guys enjoyed learning about these functional groups. I will see you next time for the next set of functional groups.